Right. Great. Welcome, everyone. I'm Rebecca Wright, Chair of Computer Science at Barnard, and we are really excited to have with us today Alex LaGrassa. Alex is a PhD candidate in the Robotics Institute at Carnegie Mellon University, researching methods that combine machine learning with classical robotics by quantifying and then expanding robot capabilities. Alex develops algorithms that equip robots with the intelligence to manipulate challenging but common deformable objects such as plants, cables, and liquid with limited access to data and computational resources. They are also passionate about inclusive STEM education so that all communities contribute to shaping technological development. And towards this goal, they lead Paths to AI Research, a mentoring program that aims to diversify AI by introducing undergraduates from a wide range of backgrounds to research. And we're really excited today to have them talking about their work on robots learning the limits of their knowledge for better decision-making. Alex.
Thank you. Great, thank you for the introduction. So my name is Alex LaGrassa, and I use they, them pronouns. This is my lab, and that's me right there. And I'm advised by Oliver Croma, who's the person in green right there. And I'm a PhD candidate in robotics at Carnegie Mellon in Pittsburgh. My research is at the intersection of machine learning and classical robotics, maybe leaning a little bit more towards the classical robotics side. And what I've been really excited about recently is plant manipulation, because it has a lot of really challenging problems within it, and agriculture is incredibly important, and deformable objects are ubiquitous in our lives. On the right is another inspiration for this work, which is one of my 5 grapevines. I have a small vineyard, and I would really like to automate some of that work there. And my research really focuses on the problem of decision-making with incomplete knowledge, which is a lot of decision-making. I'm really passionate about undergraduate research, which is how I got here today. Part of it is that it exercises some really critical skills for technological development, such as critical thinking, problem solving, and humans are naturally curious. And I believe that research is a very natural extension of that curiosity. But most importantly, we're not doing research alone. Research is really a global effort. And as part of that, the relationships we build are really core to our growth. So I think mentoring is one of the most important parts of research. I actually got to experience this for the first time in high school, where New York City Public High School taught us how to do research in our first year in high school. And that's how I ended up across the street at Columbia University doing chemistry as a 15-year-old. And I got to research the underlying chemistry of a system to understand how it affects its physical properties and participate in the research process. This was incredibly valuable for me. And as a result, I really wanted to give back. And as a PhD student, I've been focused on bringing undergrads into research so they can find their mentors through a program called Paths to AI Research, which is a mentor matching program for matching undergrads interested in AI research with grad students who can talk to them about what the process is like. And that way they can engage in research in a way that includes everybody in shaping how technology develops. To that, I think the main takeaway I would like for people to get from well, one big takeaway I'd like people to get from this talk is that computer science is for everybody. There are aspects in real world problems that everyone can contribute to. And this is also not just abstract for me, this is also quite deeply personal. I do come from several communities that are heavily underrepresented in tech. I am a queer, non-binary, neurodivergent, and disabled. And these identities have really shaped how I view research, technological development, and collaborations. As such, it is important for me that this talk is accessible to you. There will be, I may ask a few questions to see where people are at in following some ideas I think are important. And also, you're welcome to interrupt me at any point for clarifying questions, although I do ask for more discussion back and forth for that to wait until the end of the talk. Accordingly, I will move around the room a little bit, and you're also very welcome to do that as well. I will not be offended. In fact, I think it's good for engagement much of the time. And relatedly, thank you so much for setting this up on Zoom. It's another way of making these talks more accessible. I'd like to highlight some of the non-research work I do towards these values. One that I've been really excited about is this Introduction to Programming Through Robotics course. This was a somewhat ambitious attempt to bring people that have never done coding before to programming a robot to move objects in their first 2 hours. And we do this on a web-based interface so that as many people as possible can participate. And lastly, I've had the privilege of working with the Girls of Steel robotics team, which is an all girls and gender minority robotics team based out of Pittsburgh, where they build a cool robot that does some really challenging tasks for basically a sports competition. And I'm really proud of them and got to see how many of them grow over the years. So it's still then moving towards my research. Again, the crux of my research is decision-making with incomplete knowledge. We have a lot of decisions to make in our lives. So we'll think of a difficult decision that you have made recently. And much of the time for that decision, you didn't have all the knowledge that you would like to have. This is a sample scenario for people to think of. So suppose one of your classmates or colleagues is starting a nonprofit, and this is a big investment. You're not sure whether to help out with that or if you'd like to stay on your current path, perhaps in academia. In order to make this decision, you have resources available to you. You can do internet research. You can talk to people. However, making these decisions takes resources and time. So you're doing this with limited knowledge and with limited resources. Very similarly, robots also do this. They also have to make decisions, where to go, what to do, from sometimes even the low-level decisions, so what the motors do. And they have some knowledge as well, which is different from how we think. So they might have maps, they do their thinking on the computer, and they also may have some physics reasoning. But they also have incomplete knowledge. Both humans and robots make decisions the best they can with the knowledge they have available. This brings me to the main 2 questions of my research. The first is, how can robots make decisions to achieve goals with limited access to knowledge and resources, such as data and compute? And then, how can they adapt their decision-making as they have access to different sets of resources and knowledge? Sometimes it increases, sometimes it decreases. And I also am interested in thinking about how we do that as humans, so we can also learn from the decisions we make for robots. These are some of the takeaways I'd like everyone to get from the talk. First is that the idea that we in robots can learn what our limitations are in order to better achieve goals, in order to do more. The second idea is that when we have limited resources, we can combine them to be able to achieve more and to be able to do it so better. And lastly is we do learn and grow throughout our lives, and the idea of ways of expanding capabilities in order to achieve tasks and adapt to new needs. I do expect everybody to reach these talk objectives. However, there will be a couple points that may require some more background knowledge. I'll try to keep these brief, and I'll indicate that with a sneak peek icon. But the talk is geared to be accessible to all audience members. All right, with that, I'm going to go into the context for my research, which is using models for decision making. A model in this context, it's a function that looks at the state of the world, which can be, for instance, a description of all objects and positions, but it can be something more general, and then predicts, given an action that the robot takes, where the robot will end up. In this illustrative example, it's moving to the right and moving down, and then, okay, there's a bug. If it moves to the right, then we expect the robot to move to the right. So this is actually an example of an inaccurate model. When you're planning, you're deciding which actions the to take in order to achieve a goal. So suppose a robot or an agent, well, in this case, it would be you. You're deciding how to get to a location to get a cake. You might choose to take the 6 local, you may choose to take the 6 express, and that will affect how you get to the location. Your goal is generally to find a path to the goal, but you may also want to find the shortest path. For robots, yeah, so this is another example of incomplete knowledge. So we have this robot, we have the model. In this case, what action should the robot take to get to the cake? Describe with the arrows, or right, left.
Right.
Yep, just go right. Now I'm going to, so you predict that the robot will go right using your intuition. And now let's complicate things a little bit. Now there's a portal. And you don't know where the portal is going to take you. What action should the robot take to get to the cake?
Question.
Mhm.
Will the portal keep you on the grid?
Let's see. You're not guaranteed that information.
Okay, then I'm going to go the same path.
Okay, so going around. So, and with limited information, you can still make decisions to reach the goal. And this is relevant to really all of life, but especially in robotics, because knowledge of the real world is incomplete. This is that example I'm really excited about, robot plant watering. And there, how does liquid interact with plants? We don't even know that well, let alone have robots reason about it. Now we'll shift into talking about a framework for making decisions with limited knowledge. So this relies on an idea called the precondition. Raise your hand if you're familiar with a precondition from any other context. Okay, so I will describe here. So a precondition is a condition, something that needs to be true before something is used. So if you're going to drink water from a bottle, the cap should be off and there should be water inside the bottle. So these are preconditions. Models can also have preconditions. These are the conditions where you can use a model to make predictions or just to use it. In this context, more specifically, it's the states and actions where a model can be used. To make this more concrete with the portal example, you can trust the model in any space except for the one with the portal. So the portal place would be outside the model precondition. And I will give a robotics example next and then check comprehension here. So suppose we have a model where it's something you can write pretty easily in Python, where if the water is above the bowl, it will end up in the bowl. And if there's water that's outside of the bowl, then it will spill. It will go outside of the bowl. So this is an inaccurate world model. The model, let's add a plant. The model is accurate for a couple pores. So an example here is the pore where it's under the leaves. So that's in the model precondition. Where's an example of a scenario where we expect the action and state to not be in the model precondition? Where would this model not work?
Where the leaves are the umbrellas.
Yeah, so over the leaves, for example. Can anyone think of any other examples? Okay.
I was going to say, like, the cup is empty.
Yeah, that could be in this scenario. So we're making an assumption about the cup being empty. So this is model preconditions. This is kind of the core of my research. Now I'm going to get more into how we can do this in a less abstract sense. So how can we quantify the limitations of our knowledge in a way that is informed by data and that can guide decision making? The first project I'll talk about is how a robot can learn model preconditions with just a little bit of real world data. A little real world data is especially important for robots, especially with robots with water around it, because there can be something dangerous happening, or it can just be inconvenient if you have to mop up a spill. To make this more concrete, one method that I and some others have used to get traction is the idea of model deviation. So model deviation is the distance between the predicted next state when making a prediction and what the actual next state is. Then, so in the portal example, we might have expected the robot to move on to here, and then to address Brian's question, it might end up off grid. And then the deviation is one way of measuring that is with the distance. We can then define model preconditions as, in math terms, as states and actions such that the distance between the prediction and the actual state is less than a threshold. And this threshold is, it's a practical measure of how much error the system can tolerate. So this can be how much it can correct or how much is just acceptable or just some really low number. And as a result, we have a nice concrete way of defining the model precondition. So if the distance is lower than D max, then it's inside. And if it's greater than D max, then it is outside. Let's see. All right, questions about model preconditions and model deviation? All right. Rebecca, are you monitoring chat?
Yes.
Okay, thank you so much. Okay, now this doesn't. One question you might have is that doesn't seem useful, because in order to do this, we need to know what the state of the world is. And if we already know that, then why do we need the models? Well, we don't know what the state of the world is. So I frame this problem as learning what the deviation will be from data. The problem is a supervised learning problem. So that means that you have an input and you have a desired output. The input is the state and the action, and the desired output is that distance. And in your data, you do know what the next state is, and you do know the model prediction. Then this estimator predicts what the deviation will be for that state and action, which is a relatively easy learning problem in many scenarios. Then you define the model precondition as, this is the sneak peek math way of doing it. It is probabilistic, and it's the probability that the deviation is within the threshold. And then you can reason about this. Getting out of the sneak peek, another way of thinking about that is the inside is where the estimated deviation is probably lower than D max. Then outside is that the deviation might be higher than D max. Not that it necessarily is, but that it might be. And then when we're planning, we would want to only use knowledge where we know that it will be accurate, which is inside that model precondition. Oh, it doesn't show on the screen. That's interesting. Okay, I'll just have to use my hand. Now, if we're doing this and we're getting the real world data, that makes it expensive because robot data is expensive. So another thing that we care about is to be able to estimate this efficiently. In a planning problem, you have start states and you have goal states. Goal states are where you want to go, and then you might have a little bit of data. The dashed line shows what the estimate is. So right now, we can't connect these regions. The problem cannot be solved. So our goal is to expand this region. We want to do so in a way that's data efficient, so not collecting too many real-world samples. One way to do that is to ensure that it's relevant to the task. So we can do just paths to the goal or attempts to get to the paths to the goal. We also want to cover more problems, so cover a wide range of space, and we want points that are informative, that actually bring us closer to being able to achieve goals. This is a sneak peek of the intuition for it, but hopefully some of it is accessible to everyone. The key idea is that we want points that are low in estimated deviation and high in uncertainty. It's the key principle. It does get a little bit more complicated because a lot of decisions are sequential. So if there's a really informative point, but you can only get part way, and then there's a deviation, then you have not reached that point. The intuition behind one way of addressing that is to weigh the importance of those later points lower, and then hopefully it will be able to make good decisions. The way we evaluated this was to look at the success rate of achieving a task. In this case, it's a plant watering task with more data. So x-axis is effectively data, y-axis is success. And we find that when we're using our method, the top line, we're able to achieve a higher success with less data than if we don't use that reasoning about the usefulness, and if we're not finding the paths to the goal. We also try this on a real world watering task, which is why there's much more uncertainty. And we find we're able to get 80% success rate on plant watering when it was rarely able to do that before, with only that was about 4 data points. So that's a very useful thing to have. And here's an example of the robot doing one of those plans where it avoids pouring over the leaves. What we've learned from this is that it is possible to efficiently learn model preconditions using knowledge of the task and informed by what the deviation estimates are. And we're able to get that nice real world result. However, in this work, we're assuming that we can solve the problem with just one model. In the next work, I'll talk about how we can expand what the robot can do, first by adding more models, and then by adding something different with human demonstrations. The different models have different efficiencies and how it gets access to knowledge. Suppose you're assembling an IKEA cabinet. You can look at the manual, and that will give you some information, and then that will help you assemble it. It might be faster. Where'd the video go? Okay, well, but it might be faster to just watch a YouTube video. And similarly, when making decisions about water, some models are really slow. So simulators tend to be really slow. And you might have some math models that are really fast. It's just an equation. Sometimes you can learn a model to make it more efficient, and it's somewhere in between. So my research is on how we can combine these models in order to solve more problems and also do so more efficiently. Now, when we're dealing with multiple models, then the problem of, let's say there's a point that's outside the model precondition. Well, now we can add another model, and now we can solve more problems. Furthermore, we can add models of different types. So we can add a simulator which might be able to solve a large range of problems. However, we know that the simulator is slow. If we add a learned model that's maybe trained on some of that simulator data, we might have something that can solve some of those problems, but much faster. For this project, I was thinking about it in a office cleaning up, tidying up domain, where we have 2 math models, very simple. One where it's just pick and place, and one that reasons about the drawer, but the robot in the drawer, but nothing else. For more complex interactions, we could use a simulator. The complicated part about this domain is that the rod can rotate. So the math model that just looks at pick and place does not reflect that rotation, which can lead to failure. So if it plans with that assumption that it's rigidly attached, you get interesting behaviors like this, where it grasps the rod and then it accidentally unintended, closes the drawer with the rod. So that's an example of where we would want to avoid model deviation. However, when we use our method with model preconditions, we avoid that scenario. So it picks states and actions that the model is that it's accurate for, and that also achieve high success. Interesting. I just noticed that my laptop is not charging.
Maybe you just try to put a plug in. Maybe that table is just.
Yeah. All right, thank you for that. Yep, thank you. Okay. All right. Another thing that we can do is we can reason about the speed. So in classical planning, there's some algorithms that if you trial actions from a state, it will let you compute a plan to the goal, and it guarantees that you'll find the plan if it exists, and also that it's the lowest cost. So this gives you a guarantee on the quality of the plan. I was able to apply 2 tricks to switch off between models. The first trick is quite straightforward, which is for each state in action, we're predicting the next state. We just pick the fastest model such that the model is in the precondition. So if this is the fastest model, Fn, and F0 all the way on the left is the slowest, and the checks and X's indicate which, if it's in the model precondition or not. Raise 1 finger for use F0, 2 fingers for use F1, and 3 fingers for use Fn. Okay, yeah, so we want to use F1 since it's the fastest that but where the model precondition still holds. However, we can make it faster by also just prioritizing search with faster models. An example that illustrates this problem is we're trying out actions. And let's say one of them is really slow and one of them is really fast. To get these guarantees, much of the time, we need to wait for the slow model to finish computing in order to continue the search. And sometimes that can become a bottleneck. So if we can reason about when we can find optimal paths to avoid the goal, we can optimal path to find the goal without using that slow part, then we can speed up search. And the intuition for how I did this was we have a queue. So you can think of it as states that are waiting to be expanded or evaluated. We can wait for those slower points to be evaluated later when we know that it will improve the quality. So this was about how we speed up the search. So let's just make sure that this leads to high success and also is fast. So we do find that if we use both tricks, that we achieve high success compared to baselines. And we also get the speed up compared to if we don't use those tricks. So if we use the trick, we get 3 compared to just the simulator is about 100 seconds, which is about what, like a little over a 30x speed up. And here's another sneak peek. With this type of planning, you can get an optimality, you can get a upper bound on the suboptimality of the plans. And the user can specify how much suboptimality is allowed while making these computational trade-offs. Going back to the big idea, this is a way of combining incomplete knowledge in a way that gives us more reliable plans, more efficiency, and still gives us guarantees. But we're still assuming that we can solve the problem with now our current models. Sometimes it's good we can try solving a problem with a method we know, but to really grow, we need to try learning new skills. So for a while, I was a believer in always just using models for planning since we understand them well. But there was a big trend in robot learning where a robot can just learn from data, which
Because
we call
according to their
so model-based planning is what we showed before. We have a model, we send it to a planner, which gives us the action to take. But in model-free planning, we don't use a model. Instead, we have a machine learning skill that goes directly from what the state is to what the action is. And generally, one way it can work is by having a human demonstration where, given the current state and maybe some image data, a human shows what the robot should do, and then it learns what action it should take in those scenarios. Now, there's a bit of a data problem here, where if we want to have something that works more generally, then we need more data points, which can be especially expensive with humans. So having a smaller precondition and less data, but still being useful is really important. I'm going to show a demonstration of kind of the training, what the training looks like, and then the testing. So during training time, the robot plans, tries to execute its plan, and then if there's a problem, it will ask the human for help in order to patch what the deviation is with that skill. At test time, then it either plans to the goal or to be able to do the skill, then executes the plan until it can't, and then it executes the skill knowing it can. To ground this in a real example, this is for a shape insertion task. The left shows the robot planning, so kind of thinking about what it's going to do. The robot tries to fit the block into the hole, but then it finds that it's not able to complete it. And so at this point, the human demonstrator takes over and completes the task by sliding it in. That's the skill. I get it eventually. Then when we test out the method, instead of trying to go directly into the hole, it goes to the beginning of the skill, which is kind of at the corner, and then it slides it right into the hole. So we can get better performance at test time. So we get much higher reliability compared to just doing pure imitation learning or planning. With very little data, we're able to get a high success rate, again, with about 5 demonstrations here. Sometimes, if we're lucky, the robot doesn't even need to learn a skill. And this is something that this framework also addresses. So if a robot was planning with a simple handle, we can expect this plan to work. But if you switch it out with a decorative handle, sometimes it will still work. And our method evaluated how reliable that was and decided no skill was needed. In summary, we can patch model-based planning to get the benefits of both with a demonstration and with efficient use of data. However, we're still assuming that we're still using deviation to indicate whether the model is useful, which if you think about it is not always the case. And we're also not really learning more from new data, which is something that robots can do. So finally, I'll talk about some more recent work, which is on expanding what the capabilities of robots. The first is well, we can just gather more data. This problem is on if we have a simple model, a simple learned model in this case, how do we adapt it to a more complex environment? Let's say we have a simple rope model that we trained in a simulator and there's no obstacles. But we want it to be useful to hook a rope in an engine bay. We want to focus on the parts of the dynamics that it already sort of knows in order to expand it. However, we may not be able to solve planning problems yet. Now, we may have some goals where it's actually on the hook, but right now it currently can't solve the problem. This approach seeks to expand that model precondition in the adapted learned model. So that way it can solve more of those planning problems in the complex domain. The intuition for our approach is based on an idea from pedagogy. Some people call it the zone of proximal development, where when a student is earlier in their learning, they might benefit from more help or lower difficulty tasks. But if it's too difficult, they may not progress. And if it's too easy, then they may get bored or may not learn much. So the idea is to be in that sweet spot. So we do this by prioritizing learning on points that are easier. So that's described as low deviation. In the rope example, low deviation means that it's usually in free space, so it's not touching any obstacles. But in some points, it does have to touch obstacles. We'll start with some parts that are similar, which are easy, some that are difficult, and we'll start with the data in the easy region. And some points may not be useful, but we'll run into them. However, the darkness indicates how important the point is to the learning right now. Over time, by focusing on the easy points, it eventually learns more so that more points become similar, and then it iteratively becomes better at the task. However, we're not expecting this to learn over the whole space, not all transitions. There's still going to be some parts of the data that the robot is really bad at predicting. So maybe parts where it snags on the engine in some difficult places. This is where the model precondition becomes really helpful. We don't need that to be able to solve problems. We can just avoid the parts where it's snagging on the motor. We wanted to make sure that we can achieve high success with small amounts of data. So we tested success rate over data again here. The method is called focus because it's focusing on a region of space. We evaluated with mostly comparing using this focusing versus using all of the data. And we found higher sample efficiency in the engine bay task when using our method. And in a plant watering example, we also found a similar trend where it was all methods were able to learn in this case, but our method was able to do so more efficiently. So in this work, we've shown a way to do data efficient, adapting knowledge in a way that's data efficient, and that if we get more data, we can get improved performance by learning strategically. The limitation in this work is that we're expecting that there's going to be some parts of the task that are quite similar, and we're still using deviation to describe if the model is useful. This next work is a way of expanding this. It's only going to be one slide. So all of this is kind of a peek. This is really exciting work that I'm doing with some students. Oh, I should mention the last one is also a collaboration with the University of Michigan. They're great at rope manipulation. This is a project also with the same lab, different student, and he has very big ambitions. So we eventually settled on this, where we're doing task-guided model generation. we have a state. Okay, the goal is we want to get a dynamics model. We want a model to do this prediction, and we're making this model. We want the model to be efficient, so not use too much compute, but also still compute high quality plans. Our input is a description of the task. So we want something that can generate these models from a description of the task. The way we describe the task, and this relaxes that idea that deviation and success are the same. Because sometimes you can have a mistake and still make good progress towards your goal. There's a lot of problems that are like that. So this problem seeks to address that. To make it a little bit more concrete, this is a tree, and we represent the tree with a graph. And the idea is when it only needs to move one branch, we would hope that it doesn't need to model the unrelated parts of the tree with as many nodes. So this can save us on computation. In practice, this is actually really complicated, and it depends on what the model you're using is. So what we do is we have the robot practice. It tries to plan and tries to achieve tasks, and it does this a lot, and it does it in simulation. Then to do the model generation, we use a diffusion model, which is a technology you might have used to generate images based on a prompt. But instead of generating images, we're generating a model in the form of how we're simplifying this the tree. So we specify a way of simplifying it, and then that is generated in using the context, where the context is what the task is. So for this robot, the task would be, say, where the tree starts, where the robot is, and where we want the tree to end up. And so far, we have some good promising results on this, where it can get similar cost as a full model, and we can get a reasonably significant speed up when using this method. So that's just a sneak preview of a project I'm really excited about. Then finally, I'll talk about some future research ideas I would love to discuss further with people. If we are not already scheduled, you can email me. And these are all still in the idea of decision-making with limited models. So starting off, this is just kind of a high-level idea of what I'm interested in, which is the interplay between knowledge and decision-making. And all of my research focuses on adapting knowledge to changing needs and resources. Some sub areas in that first is transferring knowledge in a way that's resource efficient from task to task. And I'll go into more detail for each of these. Doing so in a way that's modular, so we can add capabilities throughout the robot's lifetime, or even throughout a technology's lifetime. And finally is in individualizing the capabilities of the robot in a way it keeps the human in the loop. So the robot can do what they want it to do, or at least so they can understand the limitations that the robot has. Really more important to me is actually the values that I'd like to have my research and other work reflect. So first is that I think I really would like to move more towards environmentally sustainable technology and other sorts of technology that benefits humanity. So this is somewhat on the application side. I also would like to lower barriers to more people participating in technology, so robotics, AI, machine learning. So I'd like to build in a way that includes more people. And finally, related to that is to use platforms, so technology that everyone has access to. So something that's low cost and open source so anyone can build. So first, this is in adapting the robot's knowledge according to new needs and resource constraints. I'm just going to describe a couple general ideas that hopefully can start some conversations later if you're interested. So first is we have a model and we want it for a specific use case. So maybe we want to deploy it onto a small device. Then we can still make it useful and shrink the model precondition. And the question is, how should we do this so that way it's still useful for the task and can still be deployed on limited compute. The next direction is in transferring from task to task. And this is something that builds pretty directly from the last project. If we have a robot that can do kiwis, how well can it work on grapes? And how can we facilitate that transfer? Or even if it's something it's very different, so recycling. And there's some technology from like the vision language models that we can leverage to make progress there. And then finally this one's more long-term, which is if we have general purpose models, how can we find a smaller version that can achieve a specific task and create more of a general framework from that. Related to this is to add capabilities in a modular manner. So we're always adding things that the robot can do. So an example is, let's say we want to do a cost benefit analysis. Maybe we want to change a component with an open source component. How will that change our capabilities? This comes from there's some communities that are really passionate about creating open source technology that interfaces nicely with each other on both on robotics side and also on the machine learning side. And there's some people that have started work on doing this, but we're really at the very beginning of having modular technology for robotics that leverages machine learning. And the second research area is in combining different forms of knowledge. So the great can take on different forms. And how can we share this type of knowledge so that way we can leverage different forms of knowledge? So I think code, for example, is a very nice way, code and natural language, of combining, say, visual knowledge and more low level tasks. And finally is how we can work together to add capabilities to a system. And so the general idea here is, let's say we have people in a robot and people have an idea of what they want the robot to do, and the robot doesn't really have an idea of what it can do, but I'd like to build something for that. But do it in a way that the robot and the human can communicate about this idea of model preconditions. There is some work on that, of showing what the visualizing capability limitations in both robotics and in broader machine learning that we can build on. And this one is a little bit more out there, which is how we can individualize what the system can do. Not only what are the limitations, but how can we move the system more towards the capabilities that the human cares about? So that way it can act aligned with their interests and with their values. And yeah, so this is the summary of some of the research areas and the common values. Clarifying questions on some of the future work. All right, so finally, I would like to thank my collaborators. I've been able to work with a lot of great people across a number of different areas and different institutions. And they've been really helpful for mentoring me and teaching me how robotics, ML research, and we're able to make these projects and many others possible. So I thank them a lot. And hopefully you've also learned something from this as well, and that we can make good decisions with limited knowledge. Humans and robots can do this. So hopefully you've gotten some of these takeaways, so ways that robots and humans can use limited world knowledge to solve tasks, how combining capabilities can bring us closer to achieving tasks with limited resources, and finally is finding strategic ways of growing capabilities to achieve tasks. Okay, yeah. So I'd love to keep in touch. If we're not already scheduled to chat today, there's different ways of contacting me. If you'd like to discuss any of these research ideas or connect on any sorts of shared values we have around inclusive undergrad research or inclusive robotics education. I'll also be at the SIGC conference later this week if anyone else will be there. That's the end of my talk, and happy to take longer questions now.
Thanks, Alex. So we have time for questions. If you're on Zoom and would like to unmute and ask your question, you can do that. You can raise your hand first and we'll call on you. Or if you want to type something to the chat, we will read that for you. And in the room, of course, you can use the traditional way of raising your hand. Go ahead.
I think that's probably a basic question, but what types of sensors do these robots typically have?
Typical is
Or actually what we see on the screen, or
oh yeah. My robots actually don't use that much, so I usually use cameras. I'll put Azure Connect cameras, preferably 2 views. These robots happen to have really good internal sensing, so they can tell where the arm is and some amount of information about the forces.
Okay. But
And
sorry.
oh, and the scales. There's to measure how much water came out. Yep. It use scales.
Oh, thank you. That's a lot.
Okay. Sensors are important.
You mentioned like the tiny ML, like deploying these on like smaller devices. What type, are you like using like model compression methods, or are you just designing like different, like smaller, solutions?
I think actually my research would probably fall more into the once you have compressed, well, starting with once you've compressed a model, describing the model limitations around that. But I think the next step is to connect the capabilities and the model compression process. So that graph network, the graph project is somewhat related to that, of what can you remove that decreases the size of the model, but also doesn't affect task performance too much beyond prediction. I was wondering, do you have a question in mind about?
Yeah, I
Or
was
system
just
in mind?
wondering if, like in that kind of goal of trying to, I guess, prune away things that, will allow you to compress, like, are you doing like quantization aware training? Are you doing like model pruning? To get that kind of lightweight kind of, while maintaining that high accuracy.
Yeah, I think it would be important to explore different ways of bringing it down. I think what would be the most interesting is connecting the what the model, especially model pruning. I think that one's something that's more straightforward of what that model affords to the task. And that way we can guide the simplification process. If we can do just the generation, that would be kind of a dream where we don't have to simplify a model. We can just start from the task and then generate the model and not have to compress anything. I don't know how to do that. That would be really cool. Hopefully we as humanity can move towards that.
Yeah, that would help with your environmental sustainability point of not creating massive models.
Yes, that is huge. Robot learning is really moving towards, we just need more data, more compute. At least my community is very, very into that. And it's really even when you go outside, when people think, well, the environmental impact of training these is significant. At conferences, actually, when people ask that question sometimes gets ignored.
I have a question for this, the part that we're talking, which I think is an important problem in learning in general, like learning from easier data points to generalize for harder examples. Can you go back to that slide, because you have two different problems and the results seem to be different, and what was the difference in the type of the easy example, or what's the difference between an easy example and a hard example? The gap between that, I think.
Yeah, this was like a very very practical way of doing it, but I think it's a good start. There we go. Okay.
In the results, if you can go to the results slide.
Oh, and the results, okay.
Yeah, it was like two different graphs.
Yeah, these are two different problems that we tried it on. The first is that bimanual rote manipulation, a rote manipulation task in the engine bay. So that's just a completely different task. So we learned completely different models. It's a different adaptation process. We just deployed, we tried the same algorithm in these two different domains.
Okay, because the nature seems to be slightly different in how the curves moves, and I was just curious in terms of what's the nature of the examples of the easy examples.
Oh, yeah. So this actually, this is a place where it diverges somewhere based on the problem characteristics. So in this problem, it was able to eventually make progress. So this was, no, I don't have an image of that one. It's pouring, but when you get it wrong, you can still make some progress, which is why all of the algorithms eventually make progress. Whereas in that real world domain, at least one of the baselines basically never solved the task ever. And that's because if it gets stuck in a particular way, or if the model precondition, so this is like we're assuming that we do not want deviation at test time. So if it cannot solve planning problems, then it's not going to execute anything. So if it never makes progress during training, it will never compute a plan under the constraints of the goal. So that does change it's a way that the problem characteristics changing how the algorithm behaves.
Do you think there's a way to understand that impact? And like pre-guess what kind of problem space you're in?
That is, oh yeah, that's also the dream. I did start a little bit of this in my master's, where it was a question of what are the problem characteristics that lead best to good performance on deep reinforcement learning. And I think one of the key challenges is in describing what the task is, describing what the constraints are. There's been some progress in describing it with you feed an image to a system that has knowledge of the planner, and then it can predict that it can solve the task itself. But you asked something that was more, there was another layer on top. Can you repeat the question, please?
Oh, I was just, it seems like what was just coming out of this conversation is that the problem characteristics have like deep impact on the performance of the approach. Right, like your approach is doing better always, but like just in general, like problem characteristics have an impact on different approaches. And I was just thinking out loud, like, is there a way, or do you have ideas about a way where you could start to, before you can start understanding like sort of the shape of the way the learning is going to go? How does, like, I give you a random problem, like, is this a good one, an easy one, a bad one? Like,
Yeah, it's that one's really interesting because there's a lot of factors at play. There's some of it comes down to the optimization problem. So a lot of it is if it's just spiky, if there's easy ways to get stuck and never make progress, then it's harder to do. And then if there's something that's more smooth, then it's more likely to make progress. So that's one, but I think broader is really difficult, especially when so spikes and spaces make problems harder. I think that's something that we can characterize as problem difficulty. There's ways you can get it at from a learning theory standpoint. For the spikiness part, there's a measure you can use of how much the function changes over a distance that you can use in some methods that make guarantees about controllers. What else? But I think for broader ones, that's quite open. And I think largely will come down to, do we have ways of specifying constraints and problems in a way that applies to a lot of problems, so we can combine knowledge about performance of those systems back to those task specifications. But yeah, that is a very, very interesting question.
All right, great. Thank you again, Alex.